Okay, so far you've seen how to do a monthly water balance, and I mentioned earlier a couple of things. The first was that you can get annual totals and then overall annual averages. So all you need to do is sum up the monthly records for each year, get an annual total, and then over all the years, you calculate an average so that you have some idea of the percentage of flow and the percentage of evapotranspiration and drainage over the rainfall on a long-term basis. Now, typically you would want to do this over many years of data. In this case, I just have 6 years. You should try to get at a minimum 10 years, but preferably much longer time periods of data to do this kind of work, which is sometimes difficult in India. Nevertheless, let's see what you get for a 5-year average in my study. I've calculated the annual averages, and first I'd like you to pay attention to this block of cells here where you have the simulated or modeled runoff ratio, which is 11.5%. That means that 11.5% of the actual rainfall was modeled as stream flow against an actual runoff ratio, which is the ratio of actual stream flow which we had the data for over the rainfall, and the actual runoff ratio was 12.3. So it's not too bad. You also can total and average the actual evapotranspiration AET. You can see it's very high, it's about 84%, and the drainage or groundwater recharge is just about 4.5%. And this is fairly typical of systems where there's a strong summer signal, deciduous forest cover. So it's good to know the overall balance. What are the different proportions of the different water balance components, what happens to rainfall, how it is proportioned. And this model can give you a quick estimate. And if you have more data, you can go ahead and use more sophisticated models than this. Some of you might be wondering how I calculated drainage or groundwater recharge. So you can use a simple water balance equation of this sort, where ds, the change in soil water, is equal to rainfall minus all the other outputs, including drainage. You turn that equation around and calculate drainage. Now I'd like to show you another kind of output you can get out of this model, which is the seasonal nature of the soil water status through the year. So in this graph, what I have is the timeline again on the x-axis. This time the data points are averages for that month over the years of data that you have. So these data points, for example, for Jan, are the average of January data over all the years. Now the red line is potential evapotranspiration, the green line is actual evapotranspiration, and the blue line is rainfall, in this case monthly rainfall. So what we find here is that soil water deficit is when actual evapotranspiration is less than potential evapotranspiration. In this case, the green line, which is less than the red line from mid-November actually to May. And this is known as a soil water deficit period because there is not evapotranspiration taking place up to the potential or maximum limit. Soil water recharge then occurs from when it starts raining enough such that it is above actual evapotranspiration and until the accumulated loss or deficit of earlier is replenished. So in this case you can see that the rainfall is beginning to exceed the actual evapotranspiration. The blue line starts rising above the green from May to August, which is when all of the loss has been replenished. after which the period of soil water surplus occurs from September to December. And the period of soil water utilization is defined as those periods when the rainfall is less than actual evapotranspiration. In our case, it occurs from December through April. So as you can see, these kinds of graphs are very useful in diagnosing the months where, for example, more irrigation would be required. And in fact, you could also calculate from our original spreadsheet an approximate amount of water that could be added and that would be needed for irrigation. But that does not form part of this tutorial right now. I think this ends what I wanted to share with you in this tutorial. I hope it's been useful to you and that you'll be able to put it to good use. Please use it with caution and use local data wherever possible. I want to end by demonstrating the importance of local data. So let's go back to our earlier graph. And I was showing you how during the first part, the first monsoon, our model does not seem to respond. And since I know that the rainfall data is quite local, I've used 3 stations and spatial averages, then let's take a look at our potential evapotranspiration data, which is the only other input that it requires. In this case, I have used the online evapotranspiration estimates that I had made and which are on the India Water Portal. This is the climate research unit-based weather data set out of which I derived evapotranspiration. And those grids are 0.5 degrees by 0.5 degrees, which is a very coarse scale data set compared to this watershed, which is a small watershed, an 88 square kilometer watershed. Hence, it's possible that the weather data is not precise enough. At the same time, the kind of data that you need to estimate evapotranspiration is very hard to come by easily. And so, since I had no weather data which was local, I was forced to use this. And in fact, this is one of the applications of those evapotranspiration estimates. I am still quite happy to get these general estimates and a hydrograph, which may not be perfect, but seems to do fairly well. So thank you, and I hope that this material is useful to you, and good luck with your own water balance modeling. Goodbye.